Hey Grandma, it's Anoushka speaking. Do you know that I'm doing the Rubber Girl Science Challenge in the intermediate category this year? Yeah, I'm 11 already. Okay, bye then. Nowadays, we take countless marvels of technology for granted, such as wireless headphones, drones, and mobile phones. However, there is one critical issue with all electronic devices. You see, each and every wireless device requires yet another charging device, and ironically, we end up with a jumble of wires for our wireless devices. This is where my Rubber Girls Major Challenge comes in. Imagine if there was an elegant solution to these endless bundles of wires. What if I was to tell you that there could be some sort of epic mechanism where the power source itself is wireless? I began to investigate the topic and found that a genius named Nikola Tesla was working on a similar problem in 1891, and he developed the first system to wirelessly transmit electricity using a high-voltage resonant transformer circuit, now known as a Tesla coil. So, I decided to construct my own Tesla coil with a twist and study its workings. Now I'm going to begin to assemble my Tesla coil. During operation, the transistor here can get quite hot, so it's important that we connect it to a heatsink, as I'm doing here. Now I'll solder the components to the PCB. Now is the time to test my Tesla coil. Lights, Tesla coil, action. As you can hear, the music is being modulated by the Tesla coils. Unfortunately, this only works at close quarters, so if I put my hand in between and provide an alternate path for the electricity as such, it stops glowing. This tiny Tesla coil has a resonant coil with a frequency-locked loop. By introducing an induced current in the secondary coil L2 into the primary oscillation circuit, the oscillation frequency of the primary loop is locked to the resonant frequency of the secondary coil, thereby maintaining resonance. The end of the secondary coil is left open, and the parasitic capacitances complete the circuit. The audio signal is used to modulate the oscillation frequency. When the audio signal is applied, the audio signal changes the primary oscillation frequency, and the resonance occurs in the secondary coil to recreate the sound fed from input. Let me now explain how the CFL lamp starts to glow. The high-voltage, high-frequency electric field causes the free electrons to accelerate and ionize the mercury gas atoms. These particles then reach the ground state, emitting UV light. This ultraviolet light is then absorbed by the phosphor coating of the CFL lamp's inner surface, then making the molecules go to a higher excitation state, as shown by this blue arrow here. Following that, through a non-radiative process, these particles transition to a lower excitation stage, as shown through the squiggly line here. Finally, through a radiative process, these particles go back to the ground state, emitting fluorescent visible light. If you really want to see the sparks fly, I visited a Nikola Tesla exhibition and saw a gigantic Tesla coil at work. I learned about resonance, Slayer-excited circuits, modulation, and the difficulty of surmounting technological challenges. I participated in this challenge because I love mathematics, science, and all types of projects. Other students should participate in the Rubber Girl Science Challenge because it's a wonderful opportunity to explore science and technology outside the curriculum. Thank you for watching. Bye!